It's my pleasure to introduce Professor Queen, or Wendy, as we all know her. This is part of a series on sustainability. You have here a QR code that you can scan and that you can use to ask questions if you wish. I'll let you do that for a few seconds while you discover what your lunch is composed of. All good? We can always go back. So I'm here to say only a few words of welcome and then also ask for an apology because I will have to run at approximately hour, having another meeting. But a few words of introduction, though, to Wendy. This is one of a series of lectures. As you can see, the topics are really quite diverse. You'll notice that's one that asks what is in our plates, and this one we now have the answer for as far as today is concerned. Today will be a talk that is, let's say, scientifically relatively, should I say hardcore? Science on porous materials. I'll say a few words about that in just a second. But first, a few words of introduction for Wendy, who earned her PhD at Clemson University in 2009, then joined NIST, the National Institute for Science and Technology, as it's now called. Used to be the Bureau of Standards, which was a fun name. Working on a National Research Council fellowship to work on neutron scattering, something she has all the time been working on. I think you've always maintained, among all the other things, a steady stream of research using neutron scattering, of which she's an expert. In 2012, she moved to the Lawrence Berkeley National Laboratory in their molecular foundry at Berkeley in California before joining us in 2015, climbing the ranks to become in 2022 an associate professor. All this in ISAC, as it's known in the acronym lingo of EPFL, or the Institute of Chemistry and Chemical Engineering. On a more informal note, I will add that she's part of a wonderful group in Sion, who are very close-knit, very productive, and fun to work with over the years. She also does a number of things. In addition to that, she works a lot in Grenoble on the beamline, still doing diffraction. She's won awards. Now, that's why I have this piece of paper, because those ones I cannot, I'm not going to go and memorize. There are too many of them. 2018, Merck's 350 Innovation Challenge. 2020, CNA News Talent at 12, which is an award which highlights, I quote, a dozen young rising stars who are using chemical know-how to change the world, unquote. And in 22, the Agora Optimus Prize from the Swiss National Science Foundation. She is, as mentioned, a very active member of the EPFL community in Sion. She animates, I think, she takes care of a lot of the work, life, etc. there of the EPFL Valais Campus Committee is what it's called. And she's now also the director of the Energy Center, something which happened after I stopped working with it, and where wonderful work has been done over the years. I see that you're both here. Thank you for coming. The talk today will be about porous materials. Now, I've worked a bit on that in totally different range. It's fun to put nothing into material. When the nothing is at a tiny scale, things become interesting because you then play at the same scale as the scale at which molecular interactions take place. And from here on, I'll let Wendy take over.
Thanks so much, Andreas. So thanks to you all for coming today. It's a pleasure to be here to tell you a bit about some of our work that's ongoing here at EPFL. Okay, now I can tell you about our work. So today I aim to tell you a bit about the world's most porous materials. I'll give you an introduction to those, and also tell you a bit about their applications, what they can do. I'll highlight really 3 applications during today's talk. How many of you have a background in chemistry? Okay, how many people hate chemistry? Yeah, okay, hopefully I can change your mind today. We design materials for very specific sustainability-related applications. So throughout my talk, you'll see these symbols to let you know, to kind of highlight the importance of the materials and their applications and helping meet these important goals. So my group is really focused on separations, okay? So by separations, I mean utilizing materials in order to separate targeted species specifically from gases or liquids. You can do it from solids as well, but normally we have to leach those solids into liquids, okay? The key is that the reason I'm very interested in separations is because they really impact a lot the world around us. Almost everything that surrounds you has been impacted by separations, from the water that you drink, the food that you're now eating, the pharmaceuticals that you consume, the materials that are going into the electronic devices in front of you, your cars, homes, sometimes the air that you breathe, okay? So I have my first pop quiz. How much of the world's energy is spent on separations? How many of you think it's 1%? How many of you think it's 5%? 15%? 40%? Okay? So those of you that guess 15%, you're correct. So a huge portion of global energy is already expended on separations, and this is without the implementation of large-scale carbon capture efforts, okay, which would probably increase this quite significantly. This stems from industrial processes. So here you see the energy consumption of the U.S. If you look, about 32% of that is related to industry, and of that 32%, 45 to 55% of that is dedicated purely to separation-based processes, okay? The reason is because they're using very energy-intensive processes like distillation. While there are new materials on the rise that can separate things like small molecules based off differences in their chemical and physical interactions, these materials are still underdeveloped. So that's really the goal of our group. We're designing materials that can be used to separate small molecules or ions in order to help potentially reduce the energy input into existing separations, or even begin to make impossible separations now possible, okay? So, just to give you some examples, there are many important separations that can have a strong impact in our world. The first, I believe, is the most important, and that is the separation of greenhouse gases from dilute gas streams. As you know, these greenhouse gases are implicated in global warming, so it's really important that we figure out how to separate those, for instance, at the source where they originate from, or, for instance, directly from air, which will help us get sparse emissions, like, for instance, automobiles, or past emissions, so that we can reach net zero or even go negative. Furthermore, we're all humans here. We know the importance of water, so it's important that we be able to remove trace contaminants from water. Unfortunately, our access to clean water is diminishing with continued climate change, and so we need to be able to account for all of these newly emerging contaminants and things in our world. Furthermore, the third separation is the separation of rare metals from ore and waste. This, of course, is extremely important. All of the electronic devices that you have in front of you have rare and critical metals inside, okay? We expend a huge portion of global energy mining these from the earth, and then we put them in devices. We're not recycling those devices and things, so right now, this process is rather linear, and this is why it's important that we begin to reduce the energy in terms of how we're extracting those from the earth, but also figure out strategies so that we can begin to recycle those metals to create a more circular process rather than the current linear situation. Furthermore, a lot of people don't know this, but for instance, there's enough uranium in the sea to supply the world with energy. The problem is that the sea is an extremely complex matrix, and so we can't get at this material. There are many others also that we can't get to because of the complexity. And last but certainly not least, the last three are related to hydrocarbons. Now these are extremely important. Most of the products that surround us are originating from these. Things like pharmaceuticals, of course, plastics, right? But also many of these molecules are used for energy, basically our energy supply, okay? And this is really, at the end of the day, part of the problems. So our solution to these problems is by the design of new materials, like the ones that I'm getting ready to introduce you to, known as metal organic frameworks. These materials are classically defined as consisting of metal ions or metal ion clusters, shown in pink. These are linked together by organic ligands shown in gray. Okay, so as chemists, we design the building blocks. We mix the building blocks in liquids. We heat those liquids up. The building blocks come together through coordination bonds and form these nice, highly porous, open frameworks. We equate these materials to sponges, albeit they're very different from sponges. They're way more porous. So here comes my second pop quiz. Okay, I've already told you they're the most porous materials in the world, and I've got 4 items here. Which item do you believe the surface area of 1 gram of material, or MOF, is equivalent to? Okay, so how many meters squared in a single gram of MOF? Do you believe it's equivalent to an iPhone 11, which is 0.027 meters squared? Do you believe it's a tennis court, which is 195.7 meters squared? A football, which is 0.15 meters squared, or a football field, 7,100 meters squared? So how many think it's the iPhone 11? Soccer ball? Football, sorry. Tennis court? See some Federer fans? Okay, and football field. Okay, some of you may have seen me talk before. Of course, it is a football field. It's quite shocking to think that 1 single gram of material can actually have the same surface area. And what this physically means is that we can just put a lot of stuff inside them. Their pore volumes are around 5 cc's per gram, or can be up to that. And so, in addition to their high surface areas, the materials have many other interesting factors, and that is their building blocks. So as chemists, we can really alter the metals, we can alter the ligands, and we can use organic chemistry to change the functionality that's present on the backbone inside the material. And this is physically how we tune those materials to get them to interact with certain targeted species that we want to remove from gases or from liquids. Okay? So these materials are quite versatile. There are tens of thousands of structures that have been reported to date with nano-sized channels that propagate in 1, 2, and 3 dimensions. Okay? Pore sizes usually range up to 2 nanometers. However, we're trying to figure out how we can work with even larger pore materials that are on the order of 2, for instance, to 10 nanometers in size. As I've already mentioned, the materials have record-breaking surface areas, and they're highly chemically tunable. So here is the prototypical metal organic framework I'll refer to as MOFs from this point forward. You can see the metal clusters here in blue. These are interlinked by these organic units shown in gray. What I note is that the materials, the walls, are really atoms thick. They're mostly open space, okay? And this is really what gives rise to these record surface areas. Just like you can access the external surface area of the material, like you can on the table, you can also access every part of the inside as well, if that makes sense. And so that's what gives rise to these record high surface areas. So as I mentioned, they're chemically tunable. If we go from this linear link now to a triangular link, we can tune the pore shape and the pore size. Imagine if we elongate that link. We can really begin to make the pore sizes quite large. Then, again, we can functionalize the link, okay? So we can change how it interacts with its surroundings, and this is physically what we're doing. Like I mentioned, one of the most important separations of our time, I believe, is carbon dioxide capture, okay? This could be from large point sources or, for instance, from air. Now, if we want to capture that CO2, we have to know where it's coming from. Here, I'm showing you 2 very large point sources. 22% of global emissions are coming from automobiles. Around 40% comes from power plants that produce the electricity we're using to heat and cool our homes. Around 8%, believe it or not, comes from cement production, okay? So what we would physically like to be able to do is go to these large point sources. We'd like to be able to install our materials and capture that CO2 before it's ever emitted into the atmosphere, okay? The problem with this is that the most mature capture technology is known as liquid amines. And I won't go through the chemistry associated with these. However, you'll see the amine here. It binds really strongly to CO2. This is one of the problems with the amines. The second is that they're really corrosive, so they're diluted with water. Materials have really, really high heat capacities. This just means that you have to put a lot of thermal energy back into the materials to re-release the CO2, okay? This is the major issue with the energy consumption, is how much you have to put in to re-release the CO2. We also have degradation processes with the amines, among other things. So if you were to implement these at a power plant, it's effectively going to decrease your efficiency by a factor of about 30%. So that means that you would have to basically use 30% more fossil fuels in order just to implement the capture technology. Okay? So this is why we're trying to find materials that can more easily release, for instance, the CO2. It's been projected that solid-based materials can do that simply because they have lower heat capacities. You have to put less thermal energy into them in order to release the CO2. So our goal is to design MOFs that can selectively grab the CO2 over other small molecules in the gas mixture. What I'm showing you here is the concentration of various molecules inside post-combustion flue gas. There are, of course, other trace impurities that are not shown. Okay? So what you'll note is that it's about 15% CO2, huge amount of nitrogen, okay? And it's at 1 bar, okay, in terms of pressure. So our goal is to design a material that has a large capacity. This just means we want it to absorb a lot of CO2. We want it to be highly selective. We want it to take up CO2, not nitrogen, okay? We want it to cycle well. So not only do we want to be able to capture the CO2, when we heat it up, we want to be able to release the CO2. And we want to do this over an extended period of time. Because if we have to replace our adsorbent, for instance, regularly, this means it's going to increase costs of our process. Furthermore, we want moderate regeneration energies. This means we don't want to have to put a lot of energy in to release the CO2, okay? So there are 2 different classes of materials that we're studying in our group. I'll only introduce you to one of them today. The first class is chemisorbents, which I'll talk about. These have amines inside. They have a reaction with CO2, so they bind CO2 very strongly. The second set are known as physisorbents. These basically bind CO2 much more weakly. And so we like to compare to see how the differences in the strength of binding energy with the CO2 impacts our process on the back end, okay? So we began taking our metal organic frameworks and infusing them with amines, okay? Because amines interact very strongly with CO2, they're highly selective. So here in black, you can see the amount of CO2 adsorbed, okay, on the y-axis here. In black, you'll see our MOF unmodified, but you'll note as we add these different amines, all the way up to this amine here, TAEA, we significantly enhance the quantity of CO2 that we can adsorb in the material, okay? And it's because the amines inside are interacting with the CO2, okay? Well, this is great, but what's the problem? Well, we only get good results for our first measurement. So after we release that CO2 and do another measurement, we see that our capacity drops by 50%. When we continue cycling the material, we see effectively that it's dropped by 85% just in 100 cycles. We need to be able to cycle these things thousands and thousands and thousands of times. So the key is that basically our amines are flying out of the pores. This is the problem. And so as chemists, what we decided to do was go in and see if we could immobilize those amines inside. So we took our material. Here you can see it has this functionality here, which is also an amine. We use this bridging molecule. It binds to it. And then we can graft the amines inside the material. So now they're completely immobilized. When we do that, you can see here our starting material that's not modified in black. Then as we increase or we add amines to it, you can see this one here, it's a low molecular weight PEI. We see a huge increase in the amount of CO2 that it can absorb, that it can take up, okay? If you look, this is showing you the quantity of nitrogen. You see that the nitrogen is really not being taken up inside the material, okay? So as a result, we can calculate our selectivities. It is over 400 times more selective for CO2 than it is over nitrogen. Nitrogen is important because it is the most concentrated element inside the gas stream, okay? So here you can see the binding energy may not make a difference to you guys, but 90 kilojoules per mole is quite strong. This is what tells us that our amine is reacting with our CO2. This is not just a weak interaction. So from what I've told you so far, I've only shown you a single component. We've looked at only CO2 and only nitrogen to see how much it absorbs, how much it takes up. Here we begin to look at these materials in gas mixtures, okay? So here you can see our gas mixture has carbon dioxide, nitrogen, with and without water. What we do, we simply stream the gas mixture through the materials. The material will grab the CO2, and the first thing that comes out of the column is nitrogen. So we watch when the nitrogen comes out, then we watch when the CO2 comes out later. The difference is referred to as our breakthrough time, the difference in those 2 time points. Okay? So here, this is what you're seeing, is the actual breakthrough. We see the nitrogen come out, and then later we see the CO2 come out, both in dry and humid conditions. You'll note that for the unmodified MOF, we only get breakthrough times of between 3 and 10 minutes, depending on how much water there is in the gas mixture. Okay? Now, when we modify this with amines, we've been able to significantly increase our breakthrough time already to 25 minutes in humid conditions. Okay? Again, here with this molecule, we see 74-minute increase, and then up to 90-minute separation time for the last one. Okay? So we've been able to improve it by a factor of 30 times just by altering the amines that we've put inside the material's pores. Okay? Now we want to see if the material cycles. So what we've done is we do the adsorption process for the CO2, 40 degrees Celsius. Then we heat that material up to around 100 to 120 degrees Celsius, and we release that CO2. So what you're seeing is weight gain because the CO2 is going in, weight loss because the CO2 is coming out, okay, as we swing the temperature back and forth. And so what you're seeing are cycles. We've cycled these up to 200 times in dry conditions, and we've done over 1,000 times so far, which is about 2 months of cycling under wet conditions. And the materials perform extremely well. So what we're doing now is we're building a pilot plant here at EPFL that will allow us to test these materials under many different process-based conditions, okay? So on this pilot plant, we have gas mixing system here on the front that allows us to make various gas mixtures that might result from different industries like cement, power plants, things of that sort. Then here on the back end, we've got 3 beds where our adsorbent goes. Basically, you can see 3 columns. They're about 1.2 meters in length. So we can put quite a lot of material in them. It'll hold kilograms of material. And then we've got an analysis system on the back end. And this is just a fancy breakthrough experiment, okay? Like what you saw in the previous setup, except this is done on a much larger scale. And this piece of equipment can let us vary different processes. It's fully automated, so it runs basically human-free. And it will allow us now, so as chemists, we are looking at things I told you like capacity and selectivity. But process engineers, when they're looking at a real separation, they're looking at other things, okay, like productivity, purity, energy consumption. Okay? And this is going to give us the opportunity to know how the parameters we're looking at, like selectivity and capacity, impact the overall performance of the material inside a given separation. Okay? And really, on the back end, this is a look at our unit. It should be installed in Valet in the next couple of weeks. We just have a building that's been completed. Basically, we're aiming to demonstrate the kilogram scale separation using our materials and also benchmarking those against state-of-the-art materials. But this is going to allow us, for the first time, to figure out the best material and process combination that gives rise to the lowest energy and economic cost. And so now we can probe those types of things, which, of course, are extremely important. So from there, we've been designing these materials for a lot of other applications, for instance, like water purification. Okay? So just like we can modify them for gas separations, we can now modify them for liquids as well. Okay? So another pop quiz. Be sure everybody's still awake. Drinking water decontamination. How much of the world's population has no access to clean water? So how many think 3%? Maybe in Switzerland. 13%? 33%? Oh, you guys are sharp. 63%. Okay. The answer is 33%. Around 1 in 3 people have no access to clean water. So if you travel throughout the world, you'll see children drinking water that's littered with harmful bacteria, heavy metals, and organics. This is not restricted to underdeveloped places. Even in developing places like China, there have been reports that show lead levels that are 20 times higher than the allowable limit based off the World Health Organization. So this reservoir is delivering water to a lot of northern Chinese cities. Okay? Then we've got the Flint water crisis in the U.S. Okay? So at Flint, there were home taps found with over 300 times the allowable limit based off the EPA standards, okay? Since this time, there have been 3,000 areas in the U.S. identified where the lead levels in children's blood is at least twice that of Flint. So this is reflecting a really big problem, okay? So our goal is really to design materials that can now grab these very toxic heavy elements like lead, like cadmium, arsenic, mercury. There are a lot of ways that you could do that. You could functionalize the metal. You could alter the linker, the ligand-based building block. What we're doing actually is a little bit different. It was inspired by some work that came out of Cornell. And so what they showed here is just a polymer, okay? What they did is they put in this blue, this is just a cyclodextrin. It's a sugar-like molecule. And then these are interlinked by rigid organic molecules, okay? What they showed, the really fantastic thing about this paper, is in the second plot, you see that it removes many of these harmful organics at a very rapid rate, okay? This is really important. Then they compared their removal efficiency of their material in blue to an activated carbon, which is a common commercially used material, and then also another material which has the same exact building blocks nearly as theirs, shown in green. What I noted is that this material in blue really outperforms the one in green that's commercially available. And I began to ask myself why, because as a chemist, we know kind of the structure dictates the function of materials. And so I began to look at these materials, and what I realized is that theirs is just more porous, okay? The surface area is around 260 meters squared per gram in what they made, versus the commercial material is around 10 meters squared per gram. So this kind of struck my curiosity. I thought, well, I've already told you that MOFs are permanently porous, okay? So what we decided to simply do is use our MOFs as a template, so to speak, where we grow polymers inside the pores. So basically what we're doing is we put a monomer inside, those monomers cross-link, form long polymer chains, and they get stuck inside the materials, kind of like a ship in a bottle, if you've ever seen one of those, okay? So then anything that gains access to the inside of the MOF can now gain access to the polymer, which has nice functionality on its backbone that can really bind these metals. It's not very easy to make polymers that are highly porous because they're not very rigid, okay? And that's kind of the point behind this. So here is our material. I won't go through it, but I will show you its performance. So we put a monomer inside, it cross-linked. We saw an immediate color change of the material, which is due to the polymerization process. Then we can see from our analysis that the polymer is actually forming in the pores. And if you take one of these particles, you put it in an epoxy resin and you just slice it, you see iron, which is a signature of the MOF, but then you see the nitrogen, which is a signature of the polymer. It is throughout the particle. So it tells you that it's definitely diffusing into the pores and forming the polymer. So let's look at the performance. Here you see the initial concentration of lead in a solution and mercury, okay? We treat that material just with our MOF. You see it drops a little. It's not fantastic. But when we treat it with the MOF polymer composite, we get below drinkable levels in a matter of seconds, just like what we saw in the work from Cornell, okay? So here you can look, the MOF reaches an equilibrium very fast, okay? But the extraction efficiency is terrible. When we modify it with the polymer, again, like I said, we're at drinkable levels in a matter of seconds. Here is plotted as a function of time on the x-axis. We can also regenerate the materials by various chemical treatment processes. And so here, then we wanted to see, well, how do they perform in really complex matrices? Okay, we'll just look at the seawater. I told you seawater is super complex. Here you can see the sodium concentration in seawater is 14,000 parts per million. We spiked it with a little bit of lead. Despite that the sodium was 14,000 times the concentration of the lead, we can still pull the lead out, and we leave behind the sodium and all of the other ions, at least within error of our experiment. So this means that our material is highly selective for lead and mercury, for instance. And that means that if we change the water, you can imagine it changes throughout the world, whatever matrix we put it in, it still performs well, okay? So then we began to compare our materials in the literature. We found that how much they can absorb, how much they can take up is really nice. The KD is just the affinity. What is the affinity of the material towards a given metal? It's very high compared to other materials. Here's our material. You can see that in the case of lead, it had the highest affinity reported to date and one of the highest capacities as well. Where we really begin to separate ourselves is in the time, the rate at which we're doing the extraction. And the reason is because the material is so highly porous. You can do the extraction very fast, whereas most materials takes minutes to hours, ours works in a matter of seconds. Then, I told you it was reversible. It's highly stable. We soak it in water for extended periods of time. We don't see any leaching of our components. And interestingly enough, it also resists clogging from various organics, which is a common problem. And we believe that the reason that this happens is because our pore sizes are actually so small that it inhibits these molecules from going inside and blocking the pores of the material. Okay? So now we're scaling the materials up. Here you can see a flow-through process that we're using for our polymerization. So here's our MOF over here. Here's our monomer here. They literally flow together on this column, which is heated. And then we pump the MOF polymer composite back out on the back end. So this is the formation. We're also developing strategies so that we can structure these fine powders into beads. So this is done in water. On the left, you had sodium alginate with the MOF. Here you can see the MOF in the sodium alginate solution. It basically forms a polymer as it hits the solution, which we're forming these nice beads. And the reason that we need to do that is because we want to study these materials under continuous flow, okay? In continuous flow, powders are actually really difficult to work with because we get huge pressure issues across our columns. Also, the fine powders are really difficult to handle, so this is why we're doing this. So here I'm going to show you the first flow-through experiment. Basically, the contaminated water goes through, comes out the other side. Okay? And we're monitoring on the back end what's coming out, right? So here I'm just showing you the lead concentration. You can see it's gradually going up. We're measuring the concentration on the back end after it's gone through the column. And then we cut the experiment off after we reach the EPA limit for lead. Okay? So this is where it's no longer deemed drinkable, so to speak. What we find is that with 1 gram of material, we can purify on the order of 10.8 liters of water, which is pretty good. Just to give you an example, most home treatment units have 60 to 70 grams of material inside. They clean around 150 liters of water, and they're said not to work around above 150 parts per billion. Our experiment was done at 4 times that concentration. So we're quite happy with these results. But something really interesting came out of this other than the material's awesome performance. Okay? And it's related to this plot here. I won't go into huge explanations, but the graduate student came into my office and showed me this. And immediately what I realized is that our polymer was transferring electrons to our metals. Okay? It's turning some of the metals into metallic state inside the material. Okay? And this is really cool because this is why we get these really super high capacities. And so then I began to look at other metals and I realized, wow, this should be really great for gold, platinum, palladium, maybe even silver. Okay? So we began looking at that, and this brings us to our third application and our third pop quiz. Okay? So this is related to now mining rare metals from ore. We're not actually doing that, we're mining it from waste. But the question is related to ore. On average, how much ore must be mined to obtain 1 gram of gold? So how many think 1 kilogram? If you guys get this one right, I'm going to be surprised. 5 kilograms? Everybody's like, 50 kilograms? 1,000 kilograms. Oh, you guys are still pretty sharp. It is 1,000 kilograms. Okay, so basically to get 1 gram, on average, of course there are higher mining grade mines, but on average you have to basically extract that from a ton of ore. Okay, so we expend all of this energy to get that out. Guess how many cell phones that makes? Anybody have a guess? Around 40. So 1 gram of gold from a ton of earth can make about 40 cell phones. So that tells you that the concentration of gold inside cell phones is way higher than it is in the ground, right? So this is why it's really important. It's also very economically viable that we start removing not just gold, but many other valuable critical metals from waste, okay? So this is, I'll show you a communications project that we have later, but this is a very, very important topic, particularly for the energy transition. So we began to design materials specifically for gold. The student made this MOF, same one. We just varied the polymers inside. And what we found is that when we took these materials, here you can see the gold concentration. When we treat it with the MOF, it drops quite a lot, 74%. But when we treat it with the MOF polymer composites, we basically are getting below our detectable limits, which is, for some of you who know, it's in the PPT regime, which is very low. This particular material, we call triple PDA, has a really high capacity. So the material can absorb around 1 gram of gold for every gram of material. Okay, so that's extremely high. It's also very fast. So we began testing it, again, in very complex matrices. So here you see a liquid containing many ions. We've spiked it with small concentrations of gold, around 10 parts per million, and huge concentrations of copper and nickel, around 850 parts per million, because these are often prevalent in electronic waste. What we note is that in green, we remove all of the gold, at least within error of our experiment. We leave behind the other metals. So we're quite happy with these materials. It's extremely fast. And now we're looking at the breakthrough. So we've taken this material, we've made our beads like you saw before, and we're doing it under continuous flow. What you see, the student has taken this CPU, he took the pins off and he dissolved those in a liquid, okay? Then he basically has a column with his material inside, these beads, and he flows that liquid through it like what you saw before. The metals, these, other than gold, break through the column. The gold is contained in the column. It absorbs a little bit of iron, but not a lot. And so here, what you can see is at this point, we've reached basically 60 weight% gold, so that means 600 milligrams of gold inside 1 gram of material. Then the extraction process begins to slow a little, but we still get up to nearly our maximum capacity of around 90 weight%. Okay? So from there, we can simply take the material, because it's a high-value target, we destroy the material, and then we're left with 23.9 karat gold on the back end, which is the highest purity reported to date, and this is partly due to the material's high selectivity. Okay? So from there, we're reaching, looking to get a lot of other targets, and I think I need to move on, so I'll skip ahead after this. But we're basically designing materials for many other metals, like, for instance, chromium. We've looked at heavy elements like arsenic. We're still working with lead, mercury, cadmium, things of that sort. We're looking at other rare metals like platinum, palladium. And so we're designing these for a variety of different applications, for recycling those from electronic waste, which you already know. We're also learning how to treat, for instance, industrial waste using these materials. Of course, surface and groundwater are of interest. And then, of course, for in-home treatment, you could use these materials as well. Okay? Beyond that, I won't talk about any of the stuff that we've done, basically some of the problems that we'll have to overcome. Maybe you guys will have questions about this. I would like to show you this. So some of our materials, I've already shown you they have really high capacities. In order to increase their capacities, we're basically trying to increase the pore size and the pore volumes of the materials. And the reason is because I think that we can get a lot more polymer inside, and we can really begin to increase our capacities quite a lot, okay? So I had this really brilliant graduate student who has begun making a lot of different building blocks for our materials, and he's developed a strategy where he doesn't have to use precious metal catalysts to make the building blocks, which makes them extremely cheap relative to previous methods, okay? He's done this, and he's made a lot of different MOFs from it, but I'll show you the important part on the back end. So with these large pore materials that have really high pore volumes, I said we could get a lot more polymer inside. So here is our original MOF polymer composite for gold extraction. If you remember the MOF itself, the capacity was around 136 milligrams per gram, so down here. After we modified it with triple PDA, the polymer, it jumped up by a factor of 4 to 5 times. Now when we go to larger pore MOFs without the polymer, look at our capacities. Already we're above that of the iron BTC triple PDA. And then when we add polymers inside of these materials, we can physically just get a lot more inside. It increases our capacities. And you can see that we've already been able to double that original value. Okay. So from there, what I've shown you is that we can really design these materials for a lot of important applications. I've shown you today CO2-based separations, toxic heavy elements, and high value and or critical commodities. I think these materials are particularly special because they have extremely high surface areas and they're highly chemically tunable. So we can change the building blocks in our MOF, the metals, the ligands. I've already shown you that. We can put various polymers inside. Then we've also developed chemistry that we can actually modify the polymers while they're inside the material's pores, which allows us to enhance their selectivity and things like that. Okay? So from there, I'll stop with the science part and tell you about another passion that I have, and that is in science communication. So we've got a Gold Rush project, which won the Agora Optimus Prize here in Switzerland for science communication. And this is basically developed out of our chemistry, or came from our chemistry that we developed specifically for gold extraction from waste, because I saw that gold is something that everybody's interested in. Switzerland, by the way, sees 70% of the world's gold. We have some of the biggest refineries in the world, so it's the perfect place to do this kind of work. And we developed Gold Rush, discover the gold in your pocket. Of course, by discover the gold in your pocket, I'm talking about your cell phone, okay? And so with this project, we're trying to teach people about the importance of recycling electronic waste and also about the unsustainable nature in which we're consuming electronics. So just so you know, in every European household, on average, there are 74 or 73 electronic devices. Of those, 13 are not in use. So they're either broken or they're just being hoarded. So it's important, one of the major issues is that people really aren't taking these to recycling centers, or of course there are people that are also throwing them in the trash. And these are extremely important because they have many different critical metals even beyond gold. So we developed a unit that is a game. We've got 6 different stations, and it literally walks you through the recycling process of electronic waste. So this was developed in collaboration with Mirko Bischofberger, who was the director of MediaCom before, and now he has a company, Science Studios. And basically this is each station of our unit. It's now in the Rolex Center, so I encourage you to go and play. The first one gives you information about the gold in your pocket and the purpose of the game. The second allows you, there's an X-ray machine and multiple devices that are moving around it. As they go across the X-ray, you can actually see inside, and it's your job as an urban miner to select which device has the most gold per unit mass. And then you can select the different parts in the device that actually has gold inside, okay? The third is Goldie, our robot. So after you've selected your device, you have to go to Goldie and you have to figure out how to disassemble it. We have different tools here, and if you don't choose the tools in the correct order, your device screen will crack, it'll knock it off the table, and you have to start over, okay? Then we have the third one, which is dissolution of your components that you've separated. So you physically have to dissolve those in a chemical. And I don't know if you guys have ever played the game Simon, right? But you have to, there's a color code, and you have to memorize that, and then you have to select it in the right color code to get your chemical mixture right, okay? And then in the last part, your sponges are dumped into this situation, which is our MOFs, and they recover it, and then you have to play basically a Pac-Man type style game in order to collect your gold, okay? Now the key is that if you perform well throughout the game, you'll be given certain pieces of golden information, which you will need to pass Station 6, okay? There's a pop quiz there, because I love giving pop quizzes, and you'll be asked a number of questions. If you've done well in the game, you should know the information in order to pass the quiz on the back end. We hope that you leave your information so that we can report to SNSF how many people are using the unit, how many people are learning stuff from the unit. Based on your performance, you'll get a golden nugget, which is virtual, but you can, engrave your name on it and rotate it around and stuff. But when you register, you also register to win various prizes, okay? So this was recently at Glattzentrum, which is the largest shopping mall in Switzerland. It was there for over a month, around 6 weeks. This is Gold Rush. Station 1, the Simon game. Goldie, our robot. You can see she picked the wrong tool. This is the X-ray machine, the Pac-Man style game where you grab your gold, and then the quiz on the back end. She's very excited, but she didn't do so well. Look at the size of her nugget. So there we gave away around 3,000 Swiss francs of gold coins, which people could use in the shopping mall. We always have an event after where we give these things away. And here you'll be able to register for, we have some gold chocolate bars, but also some real gold bars from PX Press and Ox, which is one of our partners that we work with to develop materials for. And they've given us, they're trying to develop a business model for recycling gold. So they have some really nice small gold bars, but they're worth quite a lot, believe it or not. That you could possibly win on the back end. So we've been at Glatt Zentrum from August to September. We were in San Francisco for a month. Now we're at EPFL for the next month. We go to Neuchâtel at Migros, Conte, and then we're looking for other events after. So with that, I have to say thank you for your attention. I have to thank this amazing group of scientists. Without them, I would have absolutely nothing to tell you because they do all the work. Our group dogs, the funders, of course, you for your attention, and I'm happy to take any questions that you might have.
I think this works, yes. Thank you so much, Wendy. We're very much looking forward to visit the exhibit at the pavilion here at EPFL whenever you have time. Is it there already, or when does it start?
It's already started. It just started yesterday,
okay,
so it's there for the next month.
Okay, very good. So if you want to visit the Gold Rush exhibit, please visit the EPFL pavilion just here on the campus. So just for those who do not know me, I'm Yasmine Calisesi. I'm the Executive Director of the Energy Center. I'm here to moderate the Q&A session today. I think you did a very good job. I don't see anybody sleeping. But, oh yeah, there is one question that just appeared on the tablet. Before we start with the questions on the tablet, I have one question myself, which is you mentioned the energy burden related to getting the CO2 out of the amines when you're using liquid amines. Now you're also using amines in your functionality.
Solids have a lower heat capacity than the liquid amines, so this is the reason it's effectively projected that they can decrease the energy cost by a factor of 2 just because of the differences in their heat capacities.
In the phase, okay, yeah.
So it's easier to heat the materials effectively.
Okay.
That's what it boils down to.
Thank you, thank you. Now I see there is those questions here appearing, so let me get this back. So the first question that comes in is, are there commercial MOFs used for carbon capture already available on the market?
Indeed. There are many companies that are developing throughout the world that are already producing MOFs and producing MOFs on very large scales. BASF has been producing MOFs now since, I guess, 2010 on the ton scale, and now there are many other smaller companies that are doing that. In particular, I have a friend in Berkeley who started a company it's called Mosaic Materials, that was just bought by Baker Hughes, and they have really nice materials that they've designed, metal organic frameworks with amines that are really great for capturing CO2 from, for instance, air. So those are doing quite well and bought by a rather big company, which...
Yeah, so what is the difference between such a used company and the R&D they can make and what you're doing in your laboratory? Like, are you targeting more specific applications or?
So we've been working predominantly, so I'll say that their materials, I don't know the cost because nobody will share that, right? So I don't know what the cost of their materials are, but I know that some of the organic building blocks that they're using are rather expensive. And so because of that, they've really been targeting more niche applications, you know, areas where you really need high performance materials. and you can afford to have more expensive materials. And so we're trying to effectively find strategies to make those materials cheaper. We're also looking not just, for instance, at air. We've been working a lot for post-combustion capture and things like that, which can, of course, be applied to other industries like the cement industry and things of that sort.
Thank you. Yeah, so wider applications and cheaper materials. Another question that came in, so you mentioned that current technology needs 30% of the energy generated to capture CO2. What is the percentage of your solution you expect?
So we expect that it'll at least be cut by a factor of 2. So it would be
15.
probably 15%. Let's see if it can be more. I mean, this is the point of the pilot demonstration unit. That is specifically so that we can begin to look at things like energy consumption and also compare. We're not just going to be looking at our materials, we're going to be looking at a lot of different materials. So we'd like to be able to see, how changing the material impacts the overall energy consumption and also the cost on the back end. Because of course, cost is so important. I mean, you can't implement it if it's not cheap enough, for instance, for industry.
And I mean, out of those 15%, what is still, the maybe the pumping and all that's still needed? I mean, does it include all the overall?
I don't know the exact percentages off the top of my head.
Yeah.
There's been a lot of work that breaks it down into the different components, but the regeneration is huge.
Yeah. The question continued, like, what is the theoretical lower bound for this?
Off the top of my head,
the energy consumption.
Off the top of my head, I don't know what the lower bound is.
Okay.
I mean, I can tell you. So
that's no question. I think we can live with the 15%. This is good enough. Yeah. Thank you, Wendy. Another question. What do you do with the CO2 captured by the MOF? How do you foresee the storage?
Nobody asks catalysis people where they're getting their CO2 from. So, no, that's a joke. So effectively, you could have multiple different pathways. Of course, you could utilize that CO2 for the development of, to make value-added chemicals and fuels. This is, of course, one option. The second option is for long-term storage, which, if you're familiar with the situation in Switzerland, I don't even think anybody knows how much storage capacity we actually have. I think here it's important that we develop strategies to utilize that CO2. In fact, we have a very large-scale project that I didn't talk about that is going to be implemented at an incineration facility in Valais called Inorganic. And Inorganic actually is meant to supply district heating to our campus in Valais. And so we're going there to capture CO2. You can think of it as almost reducing the CO2 footprint of the campus. But at this site, there are going to be multiple demonstration projects going on. And so beyond the capture part, we're supposed to get to 1 ton capture per day. But we also have other technologies where we will be then converting that CO2 into basically value-added chemicals and fuels, things like cyclic carbonates, methane, among other things like ethylene, which is super important for the chemical industry. I think it's produced on a 200 million ton scale per year. So I think it's the largest in the petrol industry. So yeah, utilization, storage.
Yeah, storage of energy. Exactly. Next question. Do you believe that capturing CO2 is viable? Even if the efficiency is good, isn't there a big scaling challenge to be able to treat all the quantity? A big proportion of the atmosphere in the case of the AV, I suppose it's direct capture, DAC, DAV? I don't understand. Yeah. So, is capturing CO2 viable?
I think it is, absolutely. I think we better hope that it is. I mean, so let's just look at the perspective within Switzerland. I think if Switzerland completely phases out all fossil fuels, we still have, so even if people don't want us to capture it from large point sources like power plants, for instance, but even if we phase out all fossil fuels in Switzerland, we're still going to have 12 million tons excess that we have to do something with, we have to get rid of. This comes from difficult to abate sources, like, for instance, cement industry, steel production, incineration facilities, for instance. There's
Agriculture.
Agriculture.
Yeah.
So I think, yes, it's viable. The cost is coming down. There are technologies that report reasonable cost. So I do think that it's possible. What scale that's going to be done, I have no idea. So.
There are different challenges to the feasibility. There is the material technical challenge. I guess this is the easiest one to solve, maybe. And then there are the framework problems. Yeah.
Even if with the technology development, we have to worry about its actual adoption. And so I think that can't happen without proper policy and things in place. And so I think that with regard to these large-scale problems that we face, we really need many different types of people that are working together. So.
Exactly. And shaping the market so that those things are done finally. Yeah.
We have to know what's viable from an economic perspective, and guess what? I'm far from being an economist. So.
It's about interdisciplinarity. Right, Sasha? Good. So do you have link with industrials in Switzerland or elsewhere that can start using this research?
Indeed. So a lot of the research that you've seen today was actually funded by a company here in Switzerland, Yasmine. And I couldn't show you actually the most recent results because they are patenting that. And we are intending to do a demonstration project on their site. So they have lots of demonstration facilities there. So we're intending to implement our materials there for demonstration. We're still in discussion over that, but yeah.
How much CO2 is produced during synthesis of 1 gram of MOF?
We need LCA studies for this to understand. So recently, I think we're 80% or 90% efficient based off so what we capture, I would say 10 to 20% is going back into the entire material making, the entire life cycle process is the estimate. But I didn't do it, and this is not my area of expertise, so I can't promise that that is truly accurate.
Well, that would be pretty good, I would say.
It sounds very, very good.
It's true that if you listen to Climeworks and their LCA, I don't think they consider also the synthesis of the materials. They just consider energy.
I mean, it's not so easy to, and this is why I think we need a lot of different technologies, because if you consider the scale of carbon capture, I mean, depending on the materials that you're using, in certain areas you may deplete with regard to the materials that you need, you may deplete that. And so we need different types of materials, I think, made from different things that are rather cheap. And we definitely need the LCA perspective. Again, it's super important for the interdisciplinary work. I think.
Yeah, as always, systemic understanding, not only material flows, but also, I mean, yeah, it's true. There is a current call at the moment. We need to answer. It's about net zero, and it's about still trying to reduce how to abate emissions in addition to what we suppose we will be able to do. And it's true that when you think about that, there are other, even more advanced alternatives to reduce emissions even before they happen. Now I'll jump to the next question. Is there low-tech techniques to building those MOFs?
Low-tech? I mean, I don't know what's considered low-tech, but we just mix building blocks in solution, heat them up, so that's pretty low-tech. I think they're very scalable. So, of course, we need to make more developments with regard to how we make the materials, for instance, in water, or, for instance, solvent-free. There are efforts in this area, but I haven't seen effectively when you go to solvent-free situations, a lot of times you really compromise your porosity in terms of the materials, and of course that means that you take a really big hit in terms of performance as well. And so I think that we need more efforts to really develop strategies to make these materials in aqueous-based media. And also, I would say I would really like to see more efforts in terms of recycling the materials. So interestingly enough, you know, MOFs are not really like some porous materials. You can eventually destroy them. And so once a material, partially collapses or something, there could be strategies developed for recycling that. We've worked a little bit on this in my lab, and I would like to see more effort in the field on how you take a material that's degraded and you basically recycle it and revamp it to get it back to the same performance level, for instance, that you had before.
Yeah, that would be amazing if that could be done, yeah, really. Another question, is your gold capture technology being deployed in industrial scale application?
So there's a startup that came out of my lab. I'm not involved in that. It's in San Francisco, but they are further developing these materials for commercial-based applications. And I also showed you the work, or Inox. We have a project with them, and we are helping them devise a strategy for extracting things like gold from real electronic waste solutions. So we do have at least one material that is really outperforming the state of the art, which we're very happy with. I'll tell you that the biggest issue with working in industrial waste is that it's extremely nasty. And so we've had to, even though we learn a lot from MOFs in terms of what works, we are, with some of the industrial waste, then having to re-engineer those things into other materials that are more stable, for instance, like porous polymers. And so with the refinery, because it's so nasty, they have one solution that our MOFs work in, and they have another solution that just absolutely destroys them. Mm-hmm. And so we've engineered it into other materials, and this is a way around it. So.
Yeah, big challenge to get out of the lab and go to real applications. Really.
You're really fun when you do that. It's really important to work with industry specifically for this reason, because it really helps you keep your chemistry, application relevant.
Yeah.
So to speak.
Yeah. Then you really face all problems, and yeah. The last question, fun question: where was the water taken from the Rhone? Was it taken before or after Syngenta or Gamolk or refinery?
It was taken from the Rhone, but the Rhone River doesn't have lead in it. We spiked it with lead, so no worries there. We've also checked it for mercury. There are loads of worries in Switzerland about mercury. We don't see any mercury in Rhone River water either. So, yeah.
And then there is an expert one. I'm not sure I'm going to read it right. Is it right that you absorb gold in form of tetrachloroaurate? Indeed. Yeah. And
so the key is that, this is a very important point, is that speciation changes functionality of your material. So they're asking what form the gold is in that we're capturing. So gold fluoride, for instance, is easy to reduce to its metallic state, but a lot of industries work with cyanides. Cyanides are really difficult to get, so we're working now to design materials specifically for cyanides and comparing that against the state of the art as well. So.
And so the question also has many many sentences. So you have to dissolve everything in HNO3, HCl beforehand, right? And so how does the selectivity compare with other closed shell elements like lead or mercury?
So believe it or not, I was really surprised. So it depends on the monopolymer composite that you use, of course. But we compared our material because when we get real electronic waste solutions from the industry, it has a lot of lead in it. And we are really very selective for gold over lead by far, and most of the other elements as well. I mean, it really is so selective for gold. It doesn't even take up a lot of platinum and palladium, which I was pretty surprised about. So, yeah, it's really selective for gold over lead, but it depends, of course, of which material. And this specifically stems from the fact that the gold is easier to reduce than lead. Right.
Is it also the thing that changes when you go to real conditions, or
What do you mean?
when using real waste instead of just in the lab? Is it just
everything changes.
changes?
Because the real waste because think about electronic waste. If you took every electronic device in this room and you disassembled them and you dissolved the materials, it's going to have a certain composition. Whereas if you go, to another building and you take electronic devices, it's going to have another composition because it's all dictated by what devices you have inside, right? And so this varies, and so we have to work with the refineries, and they work in really large batches so that we can be consistent with it, because even when they get different batches, it changes, right? And so yeah, from the lab settings, it's really important that we know what their compositions are so that we can then simulate that in the lab. Because if you don't, it really can change your performance a lot.
But then also with the whole the whole spectrum. Yeah.
This is why we want materials that are so selective, because it means that when you put them in different streams, they still perform well. Whereas if you have a material that's not selective, then you put it here that's got different metals, you put it there, and guess what? Your performance is gone, and you don't even know, right? So you literally have, for materials that are not selective, you really have to test them to be sure. But I think this is the niche that we have with regard to MOFs compared to many other materials is really this high selectivity. But there's not a lot of work. People don't really understand for a given metal, what environment do we need to really get that metal? And so we're trying to make vast numbers of metals, test them in these environments to figure out what functionality gives rise to this selectivity that we desire so much, if that makes sense.
Then the last question, how MOFs are better than COFs for CO2 capture? What are COFs?
Covalent organic polymers.
Okay, thank you.
We're making COFs too. I'm not against COFs. They are rather, I would say, depending on the building blocks that you use, they can be rather expensive. We found a way to make them much less expensive using the ligands that we made in our lab. So we're working with both. I don't say that there's any problem with COFs. Maybe the surface areas and things are much lower. However, COFs are going to be, really, really stable. So in some conditions, we would choose to work with COFs. In other conditions, we would choose to work with MOFs, right? MOFs are also supercrystalline, and as a chemist, I want to know why my material functions, right? And so because they have this long-range, beautiful structure, we can determine what really makes them function well, if that makes sense. And then we can engineer that into a COF. So,
very good.
It?
I think that's it for now. I still have one question.
Yep.
Have you ever computed how many kilograms of MOFs you need to remove the 12 tons
Of CO2.
So the average capacity, so good adsorbents range from maybe 8 weight% up to 20 weight% CO2. So you can imagine, it depends on how many times you're planning on adsorbing and releasing, but probably I would say 1 to 1.
Yeah.
If you want to capture a kilogram of CO2, maybe you need a kilogram of material.
Okay.
Because usually the cycling offsets the lower capacity. So
Yes, yes. So we need 12 million tons of MOFs by 2050.
Yeah, good luck.
Good. You're not out of work, Wendy. So I'd say if there are no other questions, it's almost time. I'd say we should conclude here. Thank you so much, Wendy.
Thanks all.
Thank you all for participating.